9.5 is the last topic from chapter 9. Right? After this, tomorrow we will do a review. And after tomorrow, we will do one last class concerning the IAs. If you have any questions about the IAs, I will answer them there. Otherwise, we will talk about how to pick topics and the general structure and guidelines you should follow. Right. Okay, so going to the Doppler effect. What is the Doppler effect? Well, basically, if something is emitting waves, if you can measure the waves when you're standing still and when the source is standing still, but if any of you moves, you will hear a different frequency. And you might have experienced this before when a fire truck passes by or an ambulance passes by, right? When it's coming towards you, you can hear a higher frequency. And as it moves away from you, you can hear a lower frequency, right? So something must be happening that changes the frequency of the waves. Of course, your movement doesn't really change the velocity of the waves. It just changes your perception of them. So we will see a couple of examples. First is they both are stationary, which means neither of them move. You have a source and a detector. And this is just a normal case. We call it a trivial case because it's the most simple one, right? Easy to solve. The frequency doesn't change. The wavelength doesn't change. Okay, so let's move to a more useful example, right? The first example is if the detector moves towards the source. In this case, the wavelengths don't change, right? The actual waves aren't being distorted. What is being distorted is the time it takes to hit each of the wavelengths, of the wave fronts, I mean. So the period does change. If you're moving towards it, you will hit consecutive wavefronts faster, right? The last case is when the source moves, right? Because the source is moving, there is a smaller distance between the wavefronts in the front, in the direction it moves, and there's a bigger distance between the wavefronts, right? So here, the wavelength does change. Right? And because the wavelength does change, this causes the frequency to change as perceived by this person here. For him, the waves are closer together, so he will hear them more frequently, right? And the period also changes. Right? So let's look at how to calculate the changes in frequency. First, we will look at the case of the moving source, right? So again, on the left, we see when it's not moving, how it will look like. On the right, we'll see when it moves, what it looks like, right? And we will explain what each of these variables mean. There's several ways to prove this, depending on what textbook you use. We will just use the top one for now and see if there's any differences between the other methods as well. All right, so there's some conventions to go through first, right? First, there's going to be initial frequency, right? The frequency that you perceive when no one is moving, and we call that F, right? And when something moves, right, you will hear or perceive a different frequency, so we have to have another symbol or variable for that. And in this case, we'll give it F prime, right? Just so that we can differentiate between these two. Next, you have the velocity of the wave, right? So the wave velocity will be v. So v is reserved for the wave, and this never changes, right? Once it is produced, nothing can change the velocity of the wave unless you change the medium. You have to change the gas, you have to change the pressure, temperature, right? Increase the density, which doesn't really happen. This is considered to be constant. So in green, it's constant, always. Which is the first base assumption we have to consider, right? Wave velocity is always the same. Next, there is something else that moves, which is a source, right? We have to have a variable for that. In this case, it will be u, will be for velocity of whatever is moving. If it's u sub s, it's a source. If it's u sub o, this is the observer that is moving. In this example, only the source moves, so u0 is equals 0, doesn't move, right? Okay, so let's see what happens. The source has a velocity u, s, right? So if t time passes, right, it's going to move a distance, and the distance is going to be ut. So the distance the source moves is going to be equal to ut. So let's zoom out. Correct? And what we're interested in is not just any time, right? We want to know how much it moved between two wavefronts. And I'll show you why. If you look here, first, when it was here, it produced one wavefront. So we will draw one wavefront in green, like so. This wavefront, as time passes by, moves towards the right, right? Correct? It moves to the right, but the observer is also moving towards the right, like you can see here. It moved this distance right here, right? Now, normally, if it had not moved, the wavefront would have been here, and the source would have been here. So the next wave would have been cut out in this point, right? And you will have this original wavelength, right? But because the source moved, when the second wavefront is made at this point, you have a smaller wavelength, right, in the front. And this is what we want to find out. This wavelength is going to help us find the frequency and the period and all the other things that we need. So let's move everything downwards. And we're going to give this a symbol, lambda prime. And this is going to equal to, well, first of all, it was the old wavelength, right? And you subtract exactly the amount it moved, this much, in yellow. So you're going to get the original wavelength minus u s times t. And t here is going to be the time between wavefronts. Here. Time between wave fronts, right? In other words, the original period t, right? Which is the original one, the same as the period when it's not moving. So let's replace this with that. Correct? Now we have an equation for the new wavelength. This doesn't give us a new frequency yet, right? So let's find the new frequency. If we know the wavelength, the person listening to this will perceive the wave has a velocity v. It's going to have this new wavelength, right? Because it's coming towards him. And you have to multiply it by the new frequency that he's going to hear, right? So we're going to replace these wavelengths such that you can find the frequency. Now, the new wavelength is going to equal to the velocity divided by the frequency, right? So let's do the replacements. It's going to be v divided by new frequency is equal to, and this is the old wavelength, so let's use the old frequency. The same velocity divided by the old frequency, there's no prime, right? Minus us and t, right? This is the old period, so let's replace this also with 1 over f, right? The old frequency. Now, if you want an equation for the new frequency f prime, this is probably not it, right? You want to probably get f prime on one side and everything else on the other side. So let's divide everything by the velocity and get the reciprocal. So on the left hand side, you're going to get f prime, which is what you want. And you divided everything by the velocity on the other side and you flipped it over, right? So it's going to be velocity divided by vf minus us 1 over f, like so, right? We're almost done. Let's factor out the frequency. So it would be on the bottom side 1 over frequency velocity minus us, right? And you can just multiply this by the top as well. And you get frequency is equal to the velocity divided by velocity minus us. And this is what we were looking for, an equation for the frequency, like so. And notice that this will always be smaller than 1, right? Because you're subtracting the velocity. And we will label this as source moving towards the observer. Source moving towards the observer, right? And because they're vectors, if you move away from it, it becomes a plus, right? In the opposite direction. So it doesn't matter if it's moving towards or away from it. We just make moving towards as a plus, so it's just v minus that velocity. If it moves away in absolute value, it would be velocity plus that velocity, right? And what that does is, if you're moving towards it, then this becomes less than 1, right? When it becomes less than 1, it's the final velocity is larger, higher, and you will see, because they're closer together, that's what you should do. You should get, right?